Hello and welcome to the third part of our Tutorial 1 Pytorch Basics section. So in this video, the final video of this tutorial, I'm going to go through models and optimizers in Pytorch. So how we define our models, what Pytorch gives us in that functionality, and how we can sort of define some optimizers and finally train a network using the sort of basic framework that Pytorch gives us to perform our gradient descent, as we talked about in the previous videos. So the first thing we're going to introduce is the Pytorch nn.Module. So this module is in the Pytorch neural networks submodule. This module class basically is what we inherit when we define our own modules, and it has a lot of functionality in it. It sort of works with the larger Pytorch framework when we pass it to optimizers and things like that. And it's basically what we use to contain our equation or our model, rather than say using the lambda function like we used before. It's what we use to actually define our model in it. So the two basic things that we need to create, like any class, we have our initialization or our init function where we perform any initialization that we might need. It's usually where we define our layers, as we'll see later on, for our model. And then the more unique one, the forward pass function, is basically where we define the actual equation of our model, right? The actual thing that is going to happen to our input data, right? And this forward function gets called sort of by default when we call the class constructor, as we'll see. So it's sort of by design the sort of forward pass of our function, so that whenever we want to put data through our model, we can just call our class. So the basic form of this module is very simple. We just inherit when we create our class constructor from this nn.Module, and we can also call the superclasses init function in our initialization. Like I said, as we'll see, we also define our layers here, but for this very basic example, we've just got a very simple equation where we've got some input value x, which is my input, going to multiply it by 4, add 2, and return that as our result. So I can create an instance of this class, and we perform a very simple forward pass. Like I said, we don't need to do dot forward. It gets called by default when we call this class this class instance, and we get our output 42, right? 10 times 4 plus 2. Right. So it's just a very clean way, because we often call the forward pass of our function. Just gets rid of that, makes it a lot cleaner. Okay, so as I said, we use this to actually define our model, and our model needs some parameters. So as I said, we do that in the initialization function. So we define some parameters of our model. You can see here we've introduced another sort of object or feature of Pytorch, and it's this nn.parameter. So this parameter is a wrapper. It is actually another nn.Module itself around a torch tensor, and this again has some additional functionality, but it basically tells Pytorch that this tensor specifically, unlike other tensors, is a parameter. It is something that we want to track. We want to store the gradients of, so treat it differently to other tensors. Like we saw before, when we introduced the autograd, we had to set the requires grad flag to true. For example, in parameters, that's set by default. We're telling it that these are parameters of our model. And when we pass this model instance to an optimizer later on, the optimizer knows exactly what to look for. It needs to look for parameter tensors. So we're going to define a very simple linear model here. We're going to have a weight tensor. Again, this is going to be a matrix. We're just going to perform a very simple linear model. We define it as output by input size. So input size is just the size of our input matrix. For our weights, and we're going to have a bias as well, right? That's just a fixed size of our output size. For my matrix multiplication, and hopefully if you've gone through the NumPy linear model tutorial in the previous section, you'll have an idea of what we're doing here, defining a simple linear model. But now we're doing it in Pytorch in an nn.Module class. Okay. So we can create an instance of that model. We can create some random data, so a batch of random data. So now we're getting to see some of these ideas of batched operations and batched data. So again, hopefully you've gone through the NumPy section 1 ML, talking about batches of data and multiple data points. So we've got 10 5-dimensional data points. I talk a bit about that again in the k-means clustering example in the section 1 tutorial. So we pass this input data through our linear model. Our linear model, matmul, will perform basically that operation on all of those inputs independently. That's basically how we do it with a linear model matrix multiplication. And we should get out a 10 by 1 output because we've defined our output dimension as 1. Put our forward pass of our data to our output of our model. To get our output of our model, the shape, as we can see, is 10 by 1, and we can see the output here. I talked a bit about detach before as well. Detach sort of breaks the computational graph so that it has no history of the previous calculations, and anything that happens later on won't backpropagate any further than this detach. Right. Again, hopefully what I've actually done there with the linear model makes sense, just focusing on how we're actually using the nn.Module to contain our model now, and using the parameters here. Okay, so what we defined here is basically just a linear layer, a linear model. These linear layers are incredibly common, and because of that, Pytorch, of course, has its own inbuilt version. It's already defined something that's effectively very similar to just what we've defined here for us, and so that we don't need to define it ourselves. You can access that as under nn.linear. So again, it's a class constructor, and we initialize it in the exact same way that we did with our own custom function. Okay. Some things to be aware of. Pytorch initializes the parameters of the model in different ways depending on the layer type. The linear, I think it's just from a normal distribution, similar to what I've done here, a standard normal distribution, randomly sampling. Though, if you see other layers like comms and whatnot, they initialize it to very particular ways. But again, just something to be aware of at this point, not something to stress about too much. Pytorch also includes a bias term by default. Yeah, and you can specify bias equals false when you create that class. But again, just something to be aware of. Usually you want a bias though, but just something to be aware of. So we can access the weights and bias of our layer that we've created by .weight or .bias. Again, just the same as just accessing .w.b for our custom one. So weights and bias, again, they're randomly initialized, and they should be the same. It's output size by input size. The reason for that, again, is because we're performing an affine transform here, and the actual function that it performs, the linear function, performs this affine transform, and it transposes the weights matrix before it does the multiplication with the input, right? Again, just something to be aware of. Why it's confusing that here it's sort of output size by input size, right? Again, that's why I also do the transpose here. You might look at it and think it's unnecessary, but that's just by convention. Okay, so we're basically just using Pytorch's inbuilt to just do this our linear layer. Hopefully it's not too confusing yet. So here it's just pointing out again, I touched on this in the last video, the grad of the parameters by default is none, not 0. So again, these weights and bias are initialized in Pytorch's inbuilt layer as a parameter, nn.parameter, and that by default requires grad as true, but that is initialized to none, not 0. Right? Just keep that in mind. It only gets created after the first backwards pass. And again, referring back to the previous video, Pytorch will accumulate the gradients unless we set it to 0. And we'll see that in a second. So let's move on. Let's create some random data. And what we're going to do is we're just going to make some random data, and we're just going to have a very basic function. So I've got 100 data points, 100 three-dimensional data points, so 103 vectors of size 3, right? And the sort of function we're going to do to get our outputs is just going to sum them all together to get a single value for each of those 100 points, and we're going to add a little bit of noise just to make it sort of realistic. right? I'm just printing out the first 10. So here's the first 10 vectors. So each one of these is a single data point. So we have a 3-dimensional data point, and we're just going to sum them together and add a bit of noise to get our target values. And what we're going to do is a little bit of linear regression with our linear model. Again, we sort of cover the basics of this in the NumPy section. So we can perform a forward pass of our linear model that we defined up here with this new data. And you can see we should get a 100 by 1 output, right? The output of our linear layer is a single value, and we get one of those per data point. So 100 by 1 is our output size. Here's an example of the first 10 outputs we get. At this point, it should be just completely random because we've just randomly initialized the parameters of our model. So now we're going to move on to looking at how we can train this very basic model. We've already seen AutoGrad, we've already seen how we can manually do the gradient descent, but Pytorch has a whole bunch of optimizers that will do that gradient descent, sort of simplify out a lot of those steps with the optimizers. And we've looked at just gradient descent, but there's a whole bunch of other optimizers that are sort of variants of gradient descent that sort of help with various problems that gradient descent can introduce when we're using or we're training high dimensional models. But for now, we're just going to be using gradient descent. Don't be confused by the fact that it's called stochastic gradient descent in Pytorch's implementation. Technically, what we're doing now is just gradient descent. It's not stochastic gradient descent because we're using the entire batch of data. Okay, so what we're going to do is we're going to define a loss function. So we need to define some objective that we're trying to minimize when we're doing our gradient descent, similar to what we did in the NumPy gradient descent example. You can define your own function, right? You can define a mean squared error function or just write out the equation for mean squared error when you're calculating the loss. But like the NumPy Pytorch layers, the optimizers, Pytorch also has a whole bunch of loss functions, huge number of loss functions that you can pick from, and you can just use one of those, initialize your own loss function, and just use that without having to worry about calculating that. Another thing that I pointed out in the previous video was that you can sort of define your own equations, and Pytorch will do the AutoGrad by breaking that up into the base Pytorch functions or operations, or Pytorch has defined its own equations or loss functions, and it's already got the derivative of that predefined. And the losses, like mean squared error, is one of those cases. It's already got the derivative of it defined. It's not going to work out the actual derivative. It's not going to work out, backpropagate through the square and whatnot. It's already defined the whole derivative of that whole chunk of that function, and it backpropagates through that. So another reason why you might want to use the functions rather than defining it yourself. They've got, depending on the loss, they've got checks for numerical stability and all those sorts of things. They just make it a lot easier. So the other thing we need to define is the optimizer. So the optimizers live in torch.optim, not under nn, and we're going to be using the stochastic gradient descent. It's really just gradient descent. And the two main things that we need to pass are the model's parameters and a learning rate. The learning rates are defined by default as some value, I think it's 0.1, depending on the optimizer. Depending on the optimizer, you can also pass in additional functions, but we're just going to do straight gradient descent and pass in the model's parameters and a learning rate 0.01. So you can see here that to get the parameters of the model, we do linear.parameters, and what this actually returns is a generator object. So basically it passes an object that iterates through all of the tensors of our module that are parameter tensors. So that's why we wrapped our tensor in this nn.parameter so that Pytorch knows this is a parameter tensor. And so when we do .parameters, that generator object will return, will include this tensor, this parameter tensor in its generator. And then basically what the optimizer does is loops through that generator for each of the parameter tensors and then goes, okay, what's the gradient? And now it can do gradient descent on that parameter tensor, right? That's what's going on behind the scenes. So that whole step that multiple steps we did before in the previous video of get the grad, right, then do the gradient descent, all of that is sort of done in the optimizer itself. And the way we make sure that the optimizer knows what our parameters are is because it's a parameter tensor, right? So you can't just make it a tensor and assume that the optimizer will see it. Okay. So what are we going to do in this sort of basic toy example? We've got this three-dimensional data and we just want to fit with linear regression the inputs to our one-dimensional output. This plot here, it's kind of hard to plot out three-dimensional data, but all I've done is I've taken the first dimension of each of the data points and plotted against the target output, the one-dimensional target output. So that's one dimension of the input plotted against the output. You can change this to say, maybe we pick the second dimension of our data or the third dimension of our data against the outputs. But ideally, right, these X's should be on the predictions, right? So hopefully after training, we'll see that they line up perfectly. So we've already got a prediction way up here from our model of, the random initialization of our model, what it actually predicts. So we pass that first into our loss function that we defined again up top here. And we pass in the target, the ground truths, the true values, and that will calculate the mean squared error value of our prediction. Again, this is a single value. The reduction is mean, so it takes the mean squared error over the batch, and we should get a single value out. .item converts that to a Python scalar. Another important thing that I didn't really touch on in the previous video is that .backwards only can work from a single scalar value. Pytorch's autograd only works from a single scalar value, even though we pass in 100 data points in this example. We need to convert that output into a single value that we then backpropagate from. And so the gradients, you could put those 100 data points through our model independently, and from each output calculate the loss, backpropagate that independently 100 times. But by doing it in this batched operation, calculating the loss, averaging over the batch, and backpropagating, all we're effectively doing is getting all of the gradients, if we were to do it independently, and then averaging them together. So the derivative or the gradient that we get from backpropagating from this averaged loss is just the average of the gradients. Right, hopefully that makes sense. I don't think there's any plan for Pytorch to maybe do it independently for each output. Sometimes it can be useful, but if you ever need the gradients per output, at this point, you just need to do it one by one. You can't do it in a batched way. Okay. So we're just going to do a single step backpropagation. So I've got my loss, I do dot backwards, and we can see the grad parameter of our parameter tensors is now filled with the derivatives. Again, these should be the same size as the tensor, and that's the average gradient for the entire batch. Okay, so once we do this, what do we need to do? Well, we need to do a single step of gradient descent, and we can just do that with our optimizer now. We don't have to calculate it manually with no grad block and whatnot. We just do optimizer.step, right? And that does it for us. And now we can pass the data through our model again, calculate the loss again, and with any luck, it should be lower. So we've successfully descended the gradient. We've successfully changed the parameters of our model to reduce the loss. Now, as I said in the previous video, machine learning, deep learning is an iterative algorithm. So gradient descent is an iterative algorithm. So we need to perform multiple steps until we converge to a point where we're happy with the performance of our model, right? So we basically combine these steps into a single training loop. Now, the basic Pytorch training loop I usually summarize in 5 steps. The first step being the forward pass of our model with the data, the calculation of the loss, zeroing the gradients so that, again, Pytorch doesn't accumulate. Pytorch will accumulate the gradients by default. So setting it to 0 to basically erase the memory of the previous steps. We need each of these steps to be independent. So 0 the gradients, doing dot backwards, we now calculate the new gradients. So the gradients from this point, right, for this set of inputs. And then we do our optimization step to change our parameters and hopefully reduce our loss. So those are the 5 steps: forward pass, loss, 0 grad, backwards, and step. Right. Pretty much every deep learning algorithm has those 5 basic steps. They may be more complicated. There might be a lot of sub steps to those, but those are basically the 5 main steps for a single iteration of a deep learning training loop. So we can perform those here. I'm logging the loss again. When you log the losses, again, it's good to use .item. If you don't use .item, it will log the loss as a tensor, and that loss as a tensor is connected to the computational graph. And so it's actually a lot bigger in memory. It's a lot bigger footprint in memory because it's also, you're appending the entire computational graph. So we don't really want the computational graph. We just want the value. So just do .item, breaks it away, converts it to a Python scalar. And so we're only logging the Python scalar loss. Okay, so we started out at a loss of 1.55, and we now have a loss of 8.7 times 10 to the negative 5. So we've definitely descended our gradient, and we can plot out our loss slugger. You can see we've gone right down and converged. Probably could have done a lot less steps, but now we can again plot one of the dimensions of our input data versus the ground truth predictions, and we can see that, yep, they now line up perfectly. So there we go. We've trained our first Pytorch neural network. It's a neural network of sorts. It is not a deep neural network yet because we have not yet introduced our non-linearities and our multiple layers, which is kind of where you'd start calling it deep learning. At this point, we've only really seen linear models, and it's not until the next section that we introduce our non-linear models for our non-linear function approximators. But hopefully this basics just has given you an idea or helps you understand why we use Pytorch, what it brings, and what it's useful for. It is useful for you to go over this in your own time, go through each of the steps. I kind of rushed through it a bit, but play around with it, change values, see what the output is, make sure the results match your intuitions, because it's really important to have a good basic understanding of what's going on so that you're not confused later on when we start to build and quickly add some more complicated concepts. So thanks for watching, and I'll see you in the next video.